We will now talk about a way of exploring directed graphs. It applies also to undirected graphs, but I will be illustrating it in terms of directed graphs. And it is known as depth first search. Depth first search, or DFS. In Comp 182, we talked about BFS. And BFS is breadth first search. And the way it works is that it explores a node, then it explores all the neighbors of the node. Then after that, it explores the neighbors of these nodes, and so on. Depth first search works in a different strategy. It explores a node, then it goes to a neighbor, then to the neighbor's neighbor, and so on. So it goes depth first before it explores all the neighbors. And one can think about DFS as a generalization of pre-ordered traversal of a tree. Okay, so we talked about binary trees and pre-ordered traversal of them. In pre-order, you visit the root first, then the left child, then the right child in pre-order. But that applies for trees, and here we want to talk about general directed graphs. They generalize trees, okay? So we talk about beyond trees. I will present DFS as really a skeleton algorithm, okay? What do I mean by that? I will be basically talking about DFS as an algorithm that will traverse the graph, and I will mark the nodes as visited when I visit them, and that's it. But this is really not the main use of DFS. DFS is the basis for many graph algorithms that you can implement for graphs to explore all sorts of properties of the graph. So for example, if you want to compute the degree distribution of a directed graph, you can traverse the graph in a DFS manner to find these degrees. If you want to check if a directed graph is acyclic, it does not have a cycle. If you want to compute strongly connected components of a graph, if you want to sort the nodes of the graph, all of that you can take DFS and augment it, or you can use DFS as a tool to accomplish these tasks. Okay, so when we describe DFS, it will be just, okay, we got to a node, let's mark it as visited, and that's all it does. So from a first look at the algorithm, it looks like a useless algorithm. Why are we just marking nodes visited and not? Again, keep in mind that this is just a basic algorithm. This is the skeleton of the algorithm that can be used to implement many other algorithms on graphs. So how does DFS work? Let me actually illustrate it on a graph first, and then we get to writing the pseudocode. So let's consider the following directed graph. Okay, so suppose we have a graph with 7 nodes, something like this. And let me label the nodes here as A, B, C, D, E, F, G, and the edges are like this. And let's take this one. So this is a directed graph on 7 nodes. And the way DFS works is that we're going to start from some arbitrary node, and we'll start exploring the other nodes of the graph starting from that node. And when we explore neighbors of a node, it's in an arbitrary order in general. So here, when I label the nodes in alphabetical letters, A, B, C, D, and so on, whenever I get to a node and I want to explore the neighbors of that node, I will assume that I will explore them based on their alphabetical order. So if a node has 2 neighbors, one is X and one is W, I will explore X before W. This is just a choice I'm making to illustrate the algorithm, okay? When we talk about adjacency list, there is no order. X can be visited before W, W can be visited before X, okay? So let me here start with node 1. And I can now say that, okay, node A is visited. Okay, so node A is visited. I need now to look at all the neighbors of A. The neighbors of A is only the node B, because there is only one edge to B. C and D are not neighbors of A because there is no edge from A to C or A to D. Okay, so the only neighbor of A is node B. So A was visited as the first node, then we visit the neighbor of A as the second node. Okay, so now we look at B and we look at all its neighbors. So B has two neighbors, C and D. Okay, so we will visit first one neighbor. Okay, so imagine I visit C first. Okay, so now I visit C here. So C is visited and it's visited as the third node. If I was doing BFS, then the next thing I need to visit is D, and I will be visiting it from B because it's a neighbor of B. Okay, if I was doing BFS and I'm visiting nodes from B, then I need to visit all the neighbors of B. So I visit from B, I visit C, from B, I visit D. DFS works differently. Now that I come to C, before I explore other neighbors of B, I need now to explore the neighbors of C. So from C, I go to D. Okay, so D is visited as number 4. But notice how I am visiting the nodes. From A, I took this edge. From B, I took this edge here. And from C, I took this edge. This is how I explored them. Now I look at C. C has no other neighbors. So we are done with C. And so, sorry, actually with D first. I look at D. D has one neighbor, right? So one neighbor, which is A. But A has been explored. So I say, okay, I'm done with D. Let's go back to C. I look at C. It has, in addition to D, which we just visited, it has also neighbor A, but A has been visited. Therefore, we are done with C. I trace back to B now. B has one other neighbor that we didn't visit or we didn't look at yet, which is D. But D has been visited. Therefore, I'm done with B. Okay. Then I go back to A. A has no more neighbors, so I'm done. What I'm trying to say is that the algorithm works recursively. So I visit A. Then from A, I look at every neighbor of A. For every neighbor, I repeat that exercise recursively. So I go from A to B. I look at the neighbors of B. B has C and D. But I first go to C and all of C's descendants. So I go to C. From C, I go to A and D. But A has been visited. I don't do anything about it. D has not been visited. I declare it visited. Then I go to D. And I mark it as visited. I look at the neighbors of D. Everything is done. Then I start going back from the recursive calls from D to C to B to A, and I am done with this. Okay, so we are done with this, but the graph still has nodes that are not visited, E, F, and G, because they are not reachable from A. Okay, so the algorithm continues and say now, okay, let's now look at another node that has not been visited and repeat the algorithm from there. So imagine we start from E, and now we mark E as visited, and this is node 5. And from E now I need to look at the neighbors. So I look at them as F and G. So I come to F here. F is visited as node number 6. By DFS, I look now at the neighbors of F before I look at G. F has one neighbor, which is B, but B has been visited. Therefore, we are done. Then I go back from the recursive call to E. I look at another neighbor of E, which is G. Okay, so now G is visited as number 7. Okay, and then I look at the neighbors of G in alphabetical order. The neighbors of G are C. C has been visited. There's nothing to do. Another neighbor is F. It has been visited. There's nothing to do. I'm done with all the neighbors of G. I go back to E. I look at E. All the neighbors have been visited. I am done. And the algorithm is done this way. Okay. Now, again, we use this edge from E to F. We use this edge from E to G. Now, if you look just at the blue nodes, what we end up getting from here is what we call a forest. Okay, so what we ended up getting is this. If we just focus on the blue edges, we got this one and we got this. So what we have here is a forest. Why is it a forest? Because it's a collection of trees. Look at the right side here, it's a tree from A to B to C to D. Again, these are graph theoretic trees. These are not binary search trees or anything like that, okay? Remember that a tree is an acyclic graph, okay? So A, B, C, D is an acyclic graph. It is a tree. E to F, E to G is an acyclic graph. It is a tree. We have a collection of two trees, which is a forest. Now, if you look at this, now these blue edges are what we call tree edges, okay? The blue edges here are tree edges. So we classify, when we do DFS on a graph, we classify the edges that are visited in different terms. So the edges that are used to visit nodes that have not been visited are the tree edges. So this graph, when we ran DFS in this example, it has 5 tree edges. The edge from A to B, the edge from B to C, the edge from C to D, the edge from E to F, the edge from E to G. These are tree edges. Now, there are other edges in the graph that have been used as well, looked at, but they didn't help us with much. So let's look actually at some of these edges here. So for example, if I look at this and we have the edge, for example, from C to A, this one here, C to A, we looked at this, but we didn't use it, in the sense that when we looked from C to A was already visited, so there's nothing to do. And the same thing from D to A. The same thing from D to A was used as well in this sense here. And these two have something special about them, that we are going from, if you look at the tree A to B, B to C, C to D, and if you look at A with respect to C, A is an ancestor of C, A is an ancestor of D. In the tree, in the forest, there is a path from A to C, there is a path from A to D, which basically we say that A is an ancestor of C, A is an ancestor of D. So these two edges here from C to A, that I will label in red, and from D to A, these are edges that we call back edges. Okay, they are back edges. These are edges that go back from a node to its ancestor in this forest. Okay, so we have these back edges, and these are the only back edges here in this graph, because if you look at all the edges that we have, there is no other edge of the black edges in the original graph that are going from a node to its ancestor in the forest. Now there is another type of edges that let me color them, let's say green here. So if you look at the edge from G to F, for example here, G to F here, G to F, it goes from one node to another in a tree, but neither of them is an ancestor of the other. F is not an ancestor of G in the forest. G is not an ancestor of F in the forest. Another one of those is F to B here, that we have F to B, and we have also, which one? We have G to C as well. If you look at them, neither B is an ancestor of F, nor F is an ancestor of B. Neither C is an ancestor of G, nor G is an ancestor of C. Again, I am talking in the forest itself. So these edges here, we call them cross edges, okay? They are going across, okay? They are not going forward, they are not going backward, they are going between two nodes and neither of them comes before the other. So we have these cross edges. So if you look at them, we used the F to B, and we used the G to C and the G to F. The only edge that's still left that is not characterized by any of these three types is, let's use this here, whatever it is, pink, or I don't know, what is this, purple, violet, whatever, from B to D, okay? If you look at B to D now, B to D is an edge that went from a node B to D. D is not an ancestor of B, so this B to D is not a back edge. B and D, we cannot say that that they are neither one of them is an ancestor of the other. In fact, B is an ancestor of D in the tree. So this edge from B to D, since it is going from an ancestor to a descendant, this is what we call forward edge. Okay, forward edge. So if you look at a directed graph and you run DFS, as DFS is operating, it uses some of the edges to visit the nodes. These are the three edges. Then there are all the other edges that are not used to visit the nodes, to mark them as visited. And we classify them into three classes. There are edges that in the forest itself go from a node to its ancestor. These are back edges, the red ones here. There are edges that go from a node to a descendant of it in the forest. These are the purple edges here. And there are the forward edges, and there are edges that go across. They go between nodes that neither of them is an ancestor of the other. Okay? And the last thing I want to say about DFS is that it also allows us to mark, to timestamp the nodes in terms of at what time they were visited, at what time we finished visiting them. Okay? So I'm now gonna just, for clarity, I'm gonna erase these numbers on the nodes on the top here. So let me just erase these ones. And let's actually now use, for example, again, let me actually use red here. So for every node, I will label the node with the time at which we discovered that node. We saw it for the first time. And I will also add another timestamp to it, which is the time at which we finished visiting all its neighbors. So we are done with that node. Okay. So if you think about it, that node A was discovered in the first time point. Okay. So at time t equal 1, we visited A. At time 2, we discovered B. The way the algorithm worked, at time 3, we discovered C. At time 4, we discovered D. At time 5, we have noticed that all of these neighbors are done. So at time 5, we declared that D is done. We are done with node D and all its neighbors or all its descendants. Okay, so the finish time of D is 5. Okay, so 4/5 means that node D was discovered at time point 4. And at time point 5, we finished it and started going back in the recursive call. When I go back from 3, I go to node C. Then I go to node C here, and I say, okay, C, all its neighbors have been visited. Therefore, at time 6, node C has been done. We have finished visiting it and all its descendants. So I go now to the ancestor of C in the forest, which is B. And at B, I look at all the neighbors. They have been all visited. So I declare that B has been finished at time 7. And then from there, I go back to node A and I declare that, okay, since all the neighbors have been visited, that we are done. Also, A is finished at time 8. Okay, so now we go next to E. We know that E was discovered for the first time at time 9. And from 9, we went to F at time 10. And F, we were done there and finished at 11. From there, we go back to E. And from at E, that we're not finished with E, we go to G. And G was discovered at time 12. And at time 13, we were done with G. And at time 14, we declared that we were done with E. Okay? So if we think about the DFS algorithm, it allows us to traverse all the nodes in the graph. It allows us to classify all the edges in the graph in 4 categories. And for every node, it allows us to label it with the discovery time, at what time it was discovered, and it allows us to label it with the finish time, at what point it was finished. Okay?